Good morning, everyone. Thank you, Keith. Feel free just to put the 10-minute thing up and then I'll stop and get some questions because I think it's important for people to ask questions. So I think my job apparently is to provide light relief, so I was told, get you all fired up, get you all excited about how exciting LiDAR remote sensing is. So perhaps a good way to start would be to see how much the audience knows. So I'll let you have 3 classes. I know nothing, I know a little bit, or I know quite a bit. So who knows nothing? And there's no shame, I'm not judging. Who knows nothing? Okay, who knows a little bit? That's pretty good. Who knows a lot? All right, I'll come and talk to you then. Don't I quite know why I'm here. I put myself in the middle camp, but I love LiDAR remote sensing, and it's an area that is really exciting forestry. It's exciting natural resource management in general, and I think really is an example of a remote sensing technology that's gone very quickly from research into operations. And so it's a great technology to talk to students about and to talk to government departments about and talk to industry about, because it is actually a really quick technology that's been updated. What is LiDAR? So LiDAR has been around for 20, 25 years, so it's been a while building up to the level that we're seeing it today. The original LiDAR development was around the use and development of terrain information. So the way we're using it here today was in fact one of the reasons LiDAR was originally developed. But since then, we get very accurate information about the ground surface, but we can also get very accurate information about what's on top of the ground. So we're starting to see it used more in forestry. We're also seeing it used more in urban applications, for example, looking at trees and how high they are and the shade they provide in cities. So we're really seeing it used by a wide variety of people, but ultimately it was designed originally for looking at landforms and changes in landforms. It is an exciting technology. It can be flown independent of sunlight and sometimes cloud, although we can't fly on top of a very dense cloud set. And it really is a technology that has gone very quickly from research to operations. So LiDAR stands for light detection and ranging. We often know radar, radio detection and ranging. So LiDAR sort of carries on that same acronym, but it's just using light instead of radio waves. So that's where the name comes from, and it's an active remote sensing technology. So active means that I send the pulse out and then I wait for it to come back. So radar's the same. But aerial photography or Landsat or Spot, these are passive because they're using the energy from the sun to see the reflectance. So when you've got an active remote sensing technology, you're able to control a lot more what you're doing because you send the pulse. So that's why it's a very accurate technology, because we have a lot of control over it because we have the sensor in the platform. Now, LiDAR works with lasers. Lasers are I can keep doing that for about 10 minutes until it gets tiring. Lasers are we use those in the near-infrared part of the spectrum. So most LiDARs would be around 1064 nanometers. So you and I can't see that. So when the LiDAR plane flies over, it's sending out these pulses that don't affect our eyes. And studies in Australia where they put these goggles on koalas, and then they flew low over the koalas were fine as well. So we think it's safe for all species on Earth and that it's not really impacting the eyes at all. So when it flies over, we can't see it, but it's sending out these pulses at 1064 nanometers. Principally, all of the LiDAR that we know about is aeroplane-based, and I'll touch on that a little bit later. We don't really have spaceborne LiDAR. So this is LiDAR though. We don't have a LiDAR satellite. This is, again, NASA's demonstration of how it would probably work. What it does is send a laser pulse from the instrument itself down to the ground. It then records how long it takes for that pulse to come back to the satellite. So it's fundamentally a measurement distance technology. So given that the speed of light is the same in Australia it is in Canada, we can actually go away and count how long it takes. So what this little graph is showing then is the pulse comes down and it comes back. We're counting how long that time is between that pulse going down and back. So we have that 5. What we will do is divide that by 2, because the pulse has gone down and come back, and simply dividing the pulse by 2 will give us the distance away between the satellite itself or the instrument itself and the ground. So it's a very, very, very simple technology for us to understand and for us to use, because all we're doing is measuring distance and looking at measures of distance. Now, we don't have a satellite system, so you just have to imagine that as being in a plane. In a forest, the same sort of thing is happening, but when we have the pulse coming down, this is 25 minutes in PowerPoint to get this to work. We have the pulse coming down, and then we essentially are getting all different reflections back from different parts of the forest as we go down, and then when we get to the ground, we get that big pulse on the ground surface itself, which you actually can't really see in that graph. So this pulse passes down from the aeroplane, and if there's no forest in the wave, then it will just hit the surface. If there's a forest, then you'll get little bits trickling back, and then you'll get the pulse when it hits the ground itself. When we look at LiDAR data, the data we get back, we can think of it in 2 ways. And we often talk about discrete return data from LiDAR or full waveform return data when we get from LiDAR. So I've just explained that. The pulse goes down, and then it starts to hit these objects. You can imagine that if I have got something like a forest, then little bits of pulses are coming back, coming back, coming back, coming back, and then I get my big pulse that comes back from the ground. You can see that as this type of response here, where here's my emitted pulse. So my pulse goes down, and you can see these returns coming back. The first return, this might be the very top of the tree. This might be perhaps some branches that's hitting through the tree, and then I'm getting that large pulse that I get back with my ground return. So you can see that I sort of get this different information when I come back. Now there's 2 things that I can record when I do that. I can either try to record that whole response, and that would be called full waveform LiDAR. The full waveform would be recording that whole response, the first return, the second return, and the ground return. Discrete return LiDAR would just pick the peaks of that pulse, and would go away and say, I'm just going to take the highest pulses that I get back and make a point out of that. So this would be the first return, this would be the second return, and this would be the ground return if I had a system that could collect 3 discrete returns. So again, I'm just trying to, in case I've mucked up your mind, full waveform LiDAR would record all of this as a continuous response. A discrete return LiDAR system just essentially picks the highest parts of the peak and then records those. So in this particular case, we would have 1 peak, 2 peaks, 3 peaks. There'd be 3 peaks returned by that system. Now, discrete return systems are the most common that we've had. And in the past, we used to only have 1 return. And then we had 2 return systems, then 3 return systems, and today we sort of have up to about 5 discrete return systems. So in that particular case, if there were actually 5 peaks here, the system would actually record 1, 2, 3, 4, 5 of those returns. And those 5 returns would be stored as points within the system. So the waveform then, the waveform is actually the distribution of how that return is given, and then from that we can tell different things happening within the profile as we come down. Different levels of information are returned that we can go away and record. And ultimately, a full waveform system should be able to give us that whole movement if we're passing through a forestry canopy. Now, when you're flying over bare ground, then this is less relevant, because really ultimately it's this last return that we want to see. But if there's shrubs or if there's other stuff lying on the ground, then maybe there's some additional information here that's above the ground that we can try to pull out to go away and try to find the ground surface. So LiDAR technology has come about because of 3 main enabling technologies. You can obviously see that the position of the aircraft is incredibly important, because it's the position of the aircraft that gives us that precision to know where the pulse came from, which allows us then to work out what it hit. So GPS is a fundamentally important part of LiDAR remote sensing, and so these aircraft or these satellites have GPS receivers in them, but to a very high grade. The second thing we have is the laser unit itself that pumps out these lasers. And then the third thing is what they call an IMU, an inertial movement unit, which actually just tells the plane whether it's like this or like this. So you get all of that information, you know exactly where you are in three-dimensional space, and then you have this LiDAR that's pulsing down. They're the three technologies together that go away and allow you to work out exactly where that pulse hit on the ground. Because you know exactly where the pulse was when it came out of here. It comes down, you can exactly work out based on time simply where you got that return from on the ground. So the first thing we do when we get a LiDAR point cloud back is to try to work out the terrain. So LiDAR is sending these pulses down. Now there's a few different types of LiDAR systems that I'll get to at the end, but the LiDAR system that all of the data that we're using has been collected from is a scanning LiDAR. So it scans like an elephant's trunk. Scans across the landscape, sending out pulses as it goes. And it's sending out a phenomenal number of pulses. So we're probably sending out, the systems that we use today are sending out between 80,000 and 160,000 pulses a second. So this is a phenomenal number of pulses that we're saturating the landscape with. So this landscape essentially comes back smothered in these laser pulses. So these laser pulses, when they come through the canopy, about the size of a dinner plate. So you can sort of imagine if we could see these laser lights coming down, it'd be like these dinner plates coming down all across the landscape in this scanning pattern. The plane then turns around, just like it does in aerial photography, and then scans as it comes back. And we might try to get some overlap to give us more points on the landscape, but ultimately the plane goes backwards and forwards, saturating the landscape with these pulses. So the pulse itself is 10 centimetres. That's pretty standard. We don't really play with that very much. The thing we do play with is the numbers of hits that you would get in a square metre. So if we fly the plane slower and lower, we will get more points per square metre than higher and faster. So there's always a trade-off then between how many points we want in 1 metre squared with LiDAR data. And as the systems get faster and more pulses are coming down, we see a movement towards more pulses per metre squared. Now, Alberta was a pioneer in much of this work, and so our density of our data is about 1 or 2 hits per metre, and I'm sure people will talk more about that, in that sort of level. Now, in Scandinavia, where they're trying to map every single tree individually as part of their forestry program, they're going for 10 or 12 hits per metre squared. So there is quite a variety in terms of the data that we can get out of that. But even at 1 metre, 1 hit per 1 metre squared, it's still a phenomenal increase in the amount of data that we have compared to other types of ways of getting terrain information, for example, from aerial photography. So the aeroplane's flying along, sends out all these pulses, and all these pulses come back, and then we either have those pulses recorded as individual points, or we have those pulses recorded as waveforms. So the first thing we like to do is try to work out where is the ground. So what we try to do is we look for the bottom hit, the last hit that we get from every pulse. So if we're lucky, that last pulse is the ground. So it'd be a very big singular response that comes back, and maybe there was only one. That would indicate to us that we've hit bare ground with nothing in the way. But sometimes we might get some other stuff coming up before we get the last pulse, and sometimes the last pulse may not even make it all the way to the ground. So there are circumstances where the pulse just can't get through and hit the ground itself. Now, for LiDAR, that is not as often as you would think, because LiDAR is not X-ray, so we're not X-raying our way through the canopy, but we're passing light through. And I tell my students, if I can walk into a forest and see light, it means LiDAR would be getting through as well. But you can perhaps imagine some wetland areas or huge areas of wind throw where the surface is just so covered with vegetation that it's unlikely that a pulse would ever be able to get all the way through. So sometimes the last pulse we get may not be the ground. It might be objects or parts of the canopy that are really obscuring the surface itself. So we have routines that try to do that, try to work out is this pulse that I've got really the ground, or is this pulse likely to be something that's slightly above the ground? So we try to filter these points first and then come back and say, these are the points we're pretty sure the ground is, try to go away and make a return and build a DEM from those. So here might be points and a point cloud. We would go away and we would try to fit the ground first, using the points that we believe are along the ground, and then we would go away and look at the other points relative to that base to go away and give us the relative height of the vegetation or whatever, or buildings or whatever other three-dimensional surfaces we've hit above the surface itself. So a lot of the work that we'll hear coming on about building of the wet area mapping product concerns how do you build very accurate models of the surface terrain itself. So remember, we have points. So whereas Landsat data or spot data or aerial photography is pixels of information, fundamentally LiDAR is just billions and billions and billions and billions of hits. So what we try to do is do some sort of interpolation of that surface to go away and give us this terrain-based information. So we've been doing quite a bit of work 5 or 6 years ago now, looking at different surface models that you can use to go away and build this digital terrain surface itself. And we'll hear more about the wet area mapping program after me, and they'll explain the techniques that they use to do this type of work. But many GIS people or people who are used to looking at terrain will recognize things like splines and tins and krigging. All of these are just mathematical ways of trying to build up the surface based on all of these different types of points. So this would be an example of what a GIS is trying to do. Here's my red laser pulses. They've come down to the landscape. A natural neighbour routine fits a linear fit between every single point to give you that overall surface. A spline allows it to have a mathematical response to it. A spline will always under and over predict above the maximum minimum point. Natural neighbour will never do that. Or something like inverse distance weighting will do a sort of like a weighted response to each point to go away and give you a type of surface. So there are lots of different ways that we can build our surfaces, and research over the last 10 years has looked at this to try to work out what are the best way to build our DEMs from LiDAR-based information. Now, that makes it sound like there's lots of options. There are, but the data is so beautiful and there are so many points that this issue of large artifacts just isn't there. We have so many points on the landscape, it's really just like filling in between millions and millions of dots. And these are different interpolation routines over a riparian area. You can see they're slightly different, sure, but perhaps if I gave that to you and compared it to a standard contour map, you would be amazed at the difference in detail that we would see. But different interpolation routines will give us different types of surfaces based on fitting those LiDAR observations. The work that we did at UBC sort of showed that there's our RMSE, our error. Our errors are very small, so 20 centimetres, 15 centimetres in the vertical, depending on these different surfaces that we're fitting. So it really isn't a massive, massive problem if you fit one versus the other. They all give very similar responses with the quality of the LiDAR data. How do we know how good our terrain maps are? Well, that's really a problem, because in many ways, LiDAR data is giving us the best that we can ever get. And that's certainly true under a forest canopy. It is very, very, very difficult to get more accurate three-dimensional information under a forest canopy than what LiDAR can give us. We could go and put a control point on the road, and then we could sort of survey into the forest, and we could have all sorts of surveying information. But in reality, the errors that we're carrying through are likely to be greater than the errors we would expect from the terrain model with LiDAR itself. So it is very difficult to assess how accurate it is, because the technology is just very accurate in that XYZ location. We've been doing a little bit of work trying to look at those vegetation features that I talked about. How important is the slope? How important is the vegetation cover above the terrain? How important is the structural class of that vegetation? So we've been looking at those different types of layers and then comparing that at a LiDAR data set that we have near Tofino on Vancouver Island. And we can see here, yes, there is a response to slope. So the steeper and steeper slope you get, the more errors you will have in the fitted DEM that comes in from those LiDAR observations. But again, that error is still very, very small. We also see that this is a measure of greenness from a satellite on our x-axis, and this is our error again on our y-axis. So this was an idea of, do we start to see errors in our DEM when we have very, very, very vegetated areas? And we can see here, what we're getting is a bit of a shape. Obviously, down there in our left-hand corner, there's very little vegetation. And then as we go greater, so this is not the error on the y-axis, this is the number of hits that are getting through to the ground. So numbers of hits getting through to the ground are greater at the lower greenness, because it's just bare ground or shrubs or some grass. As we start to get more and more green, we start to see those numbers of hits getting less and less and less. A little bit of a curve there, which we attribute to the fact that once you get into more old growth forest, you might in fact start to see more points coming down to the ground again. But it's this intermediate stage of very dense young forest canopies that we may not be getting penetration all the way down to the ground. This is just the same sort of thing. Again, this is structural class by density. So again, it's this young forest, pole sapling, dense forest stands that might be reducing the hits as they pass through the forest canopy down through to the ground. And then we started to see an increase in a number of hits on the ground as we move out of that stage, again, into this more open forest. So here's just a few examples, pretty pictures, I guess. There's a famous sort of example of Bainbridge Island in state of Washington that was flown with LiDAR. So you can sort of see here the DEM that we would expect from a standard shaded relief map. This would be derived from aerial photography, and then the pixels or the grain of that would come back at 10 meters by 10 meters, and then you can start to see the comparison that we would get with LiDAR technology. So it's absolutely phenomenal. Two things are happening here, though. One, to be fair, two things are happening here. One is the smaller grain. So there are a lot more pulses coming out of LiDAR than there are out of that points that would have been derived from the API. So there's a resolution aspect to the LiDAR. There's just more data. But the second thing is LiDAR is passing through the canopy. So we're actually getting a below canopy response in this DEM, where in many ways that's going to be a top of canopy based DEM from aerial photography. Now, in aerial photography, they will try to find the ground as best they can. They'll look for open patches to put their points that the DEM gets built out of. But with LiDAR, many of those hits are going to be hits that have come from the surface of the vegetation itself, the surface of the ground itself. So another example, this is British Columbia. So this is Tofino. So Tofino has some of the, the densest vegetation that we have, very, very high structural classes and leaf area. And again, you can see it's almost like an X-ray looking down onto the ground. Remembering, of course, that it's not an X-ray. We're not seeing through the vegetation in that sense. We're just peering through the gaps in the leaves. You can see why this is so interesting for riparian ecologists and people like that, is because you can actually see these tributaries much, much easier, and where they go, the orders of the streams are much more apparent from a LiDAR-based response than a response that you'd be getting from standard aerial photography. I call this remote sensing porn. So gorgeous, beautiful looking images that are just leave you absolutely astounded. So I've mentioned, so this gives you the terrain. So this was the first step, this whole process of going away and deriving your terrain model. And this is what wet area mapping then uses and moves ahead that we'll hear about following me. In a forestry context, the second thing that we would do would be to subtract all the hits that are not the ground away from the ground. So I have this massive point cloud, all of these billions and billions of points, but now I have my fitted ground surface. So all I would do in a forestry context would be I would subtract my hits that are not ground from my ground, and that will give me my relative heights above the ground, which would then be my tree heights. So I can go away and get very accurate information about the heights of the trees themselves. Now, this information also is dependent on your spacing. So in Scandinavia, I mentioned 12 hits. So they're going to see perhaps 12 hits in every single tree crown. So they might be able to count their trees. If we have less dense data, we will still see data that looks like this, but we would have less hits per individual crown. So we wouldn't really, with Alberta's data set, we don't try to count individual trees. Rather, we work at the plot scale. What is the mean height of all of the returns? And we can get a mean height of the trees within the plot. So we just sort of scale our analysis level a little bit bigger if we have less data in our point cloud. So I mentioned, I'll just jump through the different types of LiDAR, then open it to questions, because I'm sure that's a much more interesting way to get more information. There are 4 types of LiDAR. The one I've spent my time talking about is small footprint LiDAR. So that's the one that is the most common by far used around the world. In the very early days, the first types of LiDAR were in fact profiling LiDAR. And they were developed for railway lines and power lines and people who didn't really care about this landscape view. All they cared about was a single line. So these profiling LiDARs just sent out an individual pulse in one line. They were quite small, the units. They could go in a Cessna. They just flew the Cessna where they wanted to put the power line, or they wanted to put the railway, or they were looking to put a road. So that was the original work. There's papers about this in the 80s. So this was the original type of LiDAR that was originally developed. When people saw the power, they then immediately wanted to move towards, so that's this is what you would get, the aeroplane flying in a straight line. It would look like this on the side, but the data we get would be like this. Quite difficult to work out where the ground is, because you don't sort of get that spatial context of that individual line. It's also difficult to relocate that individual line in the field. You can imagine that it's very precise. So trying to work out exactly where it was can start to get a bit problematic when you've just got one single pulse. So that's really when people started to say, can we build scanning LiDARs? And that's the systems that we're all starting to use today. Instead of it being just a single pulse, we're going like this, backwards and forwards, backwards and forwards, backwards and forwards. We're going out to about 20 degrees. So that's not really an issue for terrain building. It can be a bit of an issue for forestry if you're starting to go too far out, because your pulses will start to see the sides of the trees rather than the straight down. So scan angle can be a little bit of an issue that we sometimes have to be aware of. With terrain data, getting actually to the terrain itself is a little bit less of an issue. As I mentioned, the densities are always going to be probably at 1 metre or less. Then the signals returned either as discrete points in a small footprint discrete return LiDAR with highly accurate information. The data can be collected from a small plane, but it can also be collected from a helicopter. You can see perhaps the benefit of a helicopter now, because a helicopter can go low and slow. So low and slow, more data. So that's why we see LiDAR often flow in a helicopter rather than an aeroplane. Scanning zigzag, 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 zigzag. So the wet area mapping product is a terrain model derived from this. If you had the original LiDAR data, you would have a point file, and the point file would give you a sawtooth type response like that. As I mentioned, we're now at about 160,000 pulses per second, and we're starting to see more and more points recorded in a discrete return system. Ultimately, though, what's happening is we're moving towards this more full waveform system. And today in Alberta and around Canada, many LiDAR providers will have instruments that actually have a full waveform response rather than a discrete return system. And take away the message that LiDAR is a sampling tool. We're always just sampling the landscape through these series of points. This would just give you, again, the discrete return response, millions and millions of points, lots of points coming back from the ground, some points coming back from different small parts of the, inside the canopy, and then you can clearly see in this data set individual trees and their crown characteristics. A full waveform system, the ones we're moving towards now, instead of just giving us a discrete return, we're actually seeing and trying to record this whole pulse, and then trying to record the pulse and then process that pulse to give us the information that we're seeing. Again, there's the pulses there, so what we're trying to do is go away and analyse these pulses and work out what that forest canopy is that we've looked at. It's more complicated, the full waveform data, and to be perfectly honest, the way most of us process full waveform data now is just count the peaks and make it discrete. So there's a bit of work still to be done in terms of how do you process something like this. The reality is the best way to process it is to count the peaks and use those as discrete points and then move through a discrete processing routine to go away and look at the environment. The other type of LiDAR that has been used experimentally is full waveform large footprint LiDAR. So far I've only talked about these pulses that come down like this. There is work and research being done to try to say, let's look at large footprint LiDAR. And by large footprint, I mean 20 metres or 30 metres. And this is a good system in the sense that it averages all of the LiDAR returns inside a forest. So it's giving you a much more integrated response of all of the vegetation within a plot. And so it's been related to biomass and those types of variables. It is very difficult, though, to get terrain from a full waveform large footprint, because you get a pulse back when it came back from the ground, but the ground could be sloping in that 30-metre distance. And so the application of this large footprint LiDAR, I think, is really very limited in terms of terrain extraction. It might be interesting in terms of sampling large areas of vegetation, but we're not really seeing it having too much applications in terms of terrain information. Because the small pulses, we can assume the terrain is flat within the pulse. But large pulse, large footprint LiDARs, we can't make that assumption anymore. Now, there aren't too many of these, so there's no chance that you'll get confused. There's really only two systems that exist, Slicer and Elvis. Both are experimental LiDAR systems built from NASA, so we don't often see them flying in Canada anyway. So there is no danger that you will find yourself with this data. We just don't have it. But it's an example, perhaps, of another type of LiDAR technology that gives us more information about forests, but perhaps less information about the terrain itself. So you get this larger footprint come down, and then you get a much more sort of smoothed response because you're getting all of the trees in the canopy, but you get this large return, this large pulse. And part of that is because the ground might be sloping. So trying to work out where the actual ground is in this Z dimension is quite difficult when you have this large footprint pulse. Just very quickly, the last type of LiDAR that we do start to see used a bit more in forestry and has been used a lot in mining is ground-based LiDAR. So ground-based LiDAR is the same instrument, but it sits on a tripod and it scans the hemisphere. So in forestry, we often do a full hemisphere LiDAR. So this one is like an American postbox with the middle cut out, and there's a mirror inside, and the mirror goes like this, and then the instrument turns like this. So it completely scans the whole three-dimensional part of the whole three-dimensional view of the canopy in about 20 minutes. So we get this incredibly rich information of these laser pulses being fired and then returned from all the trees and all the vegetation. The other type of ground-based design is more like a flat panel. So it looks at a face rather than tries to build the whole hemisphere. And that's what it's been used for cliffs, or sort of looking at vertical surfaces to try to look at patterns in mining and geology. We also see it used in archaeology. So, not archaeology, like when you want to preserve an old building, historical, whatever it is. But you know, you have the old building and it's falling down and they're all worried, oh, you know, is the gargoyle going to fall off? We don't know where the gargoyle came from. So they go and put the LiDAR in front of it, they stop all the traffic, and then the LiDAR scans the whole front of the building, giving this incredibly detailed sort of information about where the gargoyle was before it fell off, for example. So we also see LiDAR used in that type of context as well. So these airborne LiDAR manufacturers, often you can buy a ground-based model, and you might try to go away and collect ground-based LiDAR data if you wish as well. In forestry, it's very exciting. We get this is a three-dimensional view then, looking up. Looks like a hemispherical photograph, but the exciting thing here is that every single point is the distance. So it's not just the reflectance, it's the distance. So white means it's close. So you can obviously then automatically try to extract number of trees, width of trees, heights of trees. People are looking at the sweep and the taper and all this type of information. So incredibly detailed information, but only at one plot. So the work that's going on is how do you extract information out of this, but then how do you design a sampling scheme where you might have ground plots over the landscape, and then you'd have these airborne systems that would go away and allow you to perhaps extrapolate some of that information further. Again, another example of a ground-based LiDAR response of how it would look in a forest. And of course, this idea of linking the airborne response to a ground-based response. So my PhD student did this. I thought it was quite phenomenal. I said, okay, good enough, get out of here, you're done. This was the ground-based LiDAR response, and then this is the airborne LiDAR response put on top. So it proves how accurate the data is that you can just call up a viewer and do something like this without having to worry too much about it. I think it does demonstrate nicely. Now, there's no ground hits here on the airborne, so there would be lots of white dots along here. They've just been removed. But it does give you an idea, I think, of we aren't collecting too much of our intermediate parts of a forest canopy in this particular case. We're getting lots of above ground hits, we'd be getting quite a few hits down here on the ground, but we can capture some information, but not all of what's happening in that intermediate part of a forest stand. Different levels of thinning will give us different level. You can see with ground-based LiDAR, this is the Mackay thinning trials in Alberta. You can see, obviously, we're getting quite different responses of returns based on the structure that we're seeing in the stand. When we do our LiDAR analysis in forestry, I just have a few examples of how you process the data. I've talked about individual trees. This is pretty ambitious to try to do this. This is what they try to do in Scandinavia. We don't, in Australia, in Canada, we often don't fly our LiDAR data this dense, that we don't really try to go after individual tree attributes, principally because we don't manage our forests on an individual tree basis. So we don't, in Scandinavia they name their trees, for God's sake. So, I mean, there's no real reason, we don't sort of manage our forests like that. So if we did, you know, Bertha, Mary, John, so you could go work out the height of each one. But in Canada and Australia, we sort of work much broader. Individual tree level, we could get individual tree height. We can go away and try to get individual crowns and try to map the individual crown if we wished. But really, the way we do LiDAR in Alberta and most places is to look at things at the plot scale. Plots give us more of this broader information about what's happening in the forest stand. One of the first things we can get very easily is cover. So I think of a sponge cake where you have different levels of the forest canopy. Or LiDAR is fantastic because all we do is we ratio the hits that come into the sponge cake versus come out of the different layers. So let's imagine our sponge cake is cake, cream, jam, and cake. So if the cake is our overstory, we would have all the hits coming in at the top of the cake, and then we'd look at the hits entering the cream, and then we'd ratio, it was going to blow my mind, we're going to ratio the hits going into the sponge, ratioed over the hits going into the cream, and we would get a very accurate calculation of the overstory cover. So LiDAR, by giving us all of these hits, really is able to give us these very accurate estimates of cover as well. So we see overstory cover, mid-story cover, and then we can try to predict these layers of the vertical part of the canopy itself from the LiDAR returns. The other way we look at LiDAR data is we have this pulse. This pulse passes through the canopy like that. The most common way we try to summarize that information is using percentiles. So with percentiles, we have our point cloud. We go away and we work out what height is the first 10% of the data. What height is the first 20% of the data, the 30%, the 40%, the 50%, the 60%, the 70%, the 80%, the 90%, and 100%. So we see that different height levels are telling us very much about where most of those returns are based within the canopy. And these metrics are the way that most of us are trying to go after more integrated variables in the forest. So biomass or volume, the way we often do that is we have biomass and volume as our dependent variable, and our regression equation simply becomes the heights at the different percentiles. So these percentile values that we're getting out of this thing become different variables that go into these regression equations, and that's how we can go away and predict biomass, volume, and these types of forestry attributes that we get across the forest canopy. And volume and biomass might be highly relevant for production issues, but we could also go away and try to predict structure or gaps or openings or complexity. And these different types of things would be related then to animal use of the forest canopy itself.